Hi everyone, myself Arijit Banerjee and I am a faculty at the University of Illinois Urbana-Champaign. Today I'm very excited to show you our final product which we have been working on for last 2 years almost in terms of developing an educational kit for power electronics. If you think about it, lots of students in the world get to learn power electronics, its theoretical aspects, and get to see these beautiful equations, forms, waveforms, and so on, mostly from a theoretical standpoint. But one of the important aspects of power electronics is the hardware. And unless and until we play with the hardware, I use the word play because it is magical. If we really play with this hardware of power electronics, there are so many details we can learn, not just in power electronics, but in signal processing, analog circuits, digital platforms, coding, you name it. There is always this interconnection between power electronics and the rest of the ecosystem for knowledge. That fascinated me, and this kit has been developed under that foundation of when a student explores this kit. It's not about doing some particular labs like a cookbook. It's not about can the students do step 1, 2, 3, 4, 5 and write a report and submit. It has been always in our vision that can this kit lead to curiosity in students' mind? Can this kit be able to see, or can the students see that, okay, there are simple structures which can do enormous amount of things if configured externally in a proper way. So here I am. This is the final kit we have so far. It has so many components in it, but let me try to uncover this a little bit. First of all, it is USB powered. So what it means that you can take this kit wherever you want, and if you have a computer with yourself, basically you should be able to run this kit on its own. All it is getting is power from the computer right now. Okay, and once it's powered up, it has different parts in it. All of these parts we will gradually build up, trying to understand what each of these components do. So particularly the blue board here, it does most of the signal processing in the analog world, whether we are trying to generate PWMs, whether we are trying to do dead times and so on. So we will try to understand that through different lab modules. On the other part of it, there is a control section. So if we are interested in designing control in the analog platform, we will be able to explore that with this kit. On the red board, we have a half bridge which is configured in a way such that you can look at different layers of the kit. So it can be whether you are looking at the device characteristic. Can we look at the Miller plateau? Can we understand switching characteristic of a MOSFET? All the way from there, and how does it impact loss and efficiency? And all the way from there, can we try to configure these devices into a form so that it can create topologies? Can we create buck converter? Can we create boost converter, buck boost converter? Can we create inverters? So we can look at those specific topologies. The next layer is we can configure the blue and red board together so that now we can start looking at the control aspects of it. Can we do voltage mode control? Can we do current mode control? And so on and so forth. So we get to an understanding of the control aspects of in an analog world. It comes with a digital platform, or the recommended digital platform is Arduino, to keep it low cost and widely accessible. It's a platform for hobbyists. So literally the barrier to entry of thinking about digital control is super low. And of course, these days with AI tools available all over the place, writing a code has become much simpler than when someone has to really think through and understand all the libraries and everything together. The first version of the code can be written by an AI tool like ChatGPT, and we can refine it based on the performance of the code. So that's part of this one. Of course, someone can replace this Arduino with a more realistic and real world microcontrollers. Plenty of them are available and it can be used, but that understanding can be preserved even if we use simple microcontrollers like Arduino. In addition to that, the kit already provides a load box. Now, many times with my interaction with faculty around the world, one of the challenges I have seen is that the loads are not standardized. So, okay, how do I put a load and so on? So, this comes with a resistive load, and of course, it has switches in it. So, if you want to do any load transients or anything on that nature, we can configure the kit, make connections, and we can look at it as it is. On the left side, this part is very interesting to me because when I was a student, when many of you were a student, power electronics always in the lab remained very ideal. Let me explain. So it has been like, okay, I have a DC source, a lab bench power supply. I run my converter, and then here I have a resistive load where I'm dumping the power, and I understand the basic performance of the converter, whether I'm looking at the steady state or transients and so on. I can take a understanding the details of it. But this keeps the student away from the realistic applications, which is the key. In my opinion, understanding realistic loads and sources becomes much exciting, and students get to see the end objective of what we are doing, why we are doing. So in that regard, this part of the kit is mostly configured with realistic loads and realistic source. So let me explain. So this blackboard here allows the kit to be configured as a DC to AC converter. And of course, students will learn gradually the different aspects of DC to AC conversion, but some part of the board is dedicated for audio signal processing, because audio is one of those fascinating application of power electronics, Class D audio amplifier, where we have to supply power to an audio speaker and students can get to see it. Or there are realistic loads like LED. Okay, so I can literally connect my kit to a power supply, which will be eventually configured using our own board power supply. So right now, if I configure this kit, as you can see, I can understand, and if I connect it to a voltage source, I can understand, okay, what's really happening if I measure the voltage, which is shown in the yellow waveform here, DC supply, nothing fancy, and a lab bench power supply, and I connect it to I'm measuring the current which is going through this LED. Obviously, you can't see it right now in the time scale we are talking about. This is a slow time scale process, but those LEDs are heating up, right? And as the LEDs are heating up, the voltage drop across the LED is going down. So unless there are protection mechanisms and resistors around it, the current will start going up. So that starts the conversation of why do we need an LED driver. I can change this and I can make it to a fan. So that's another electromechanical energy conversion system. And as you can see here, I'm drawing some current here from this fan, and I can change the fan speed or fan loading based on the mechanical vane, right? Why do I need power electronics to run a fan? Why is it more efficient to run a motor drive system using power electronics? Something to think about. It's a realistic load again. And going back to the audio, well, I can connect the audio signal and I can start thinking about what is a speaker really look like. Is it a constant resistance like what we think of, or is it beyond that? So if I look at the speaker, well, I'm sending some current here or sending some voltage here, and as I change this, I need a AC signal. How do I generate that? And how do I preserve the quality of my sound? All of these aspects can be studied using this educational kit. Not only that, we can also connect this kit to a solar panel, okay? And we can look at what is an non-ideal source. So a solar panel, is it a constant voltage source like a lab bench, or is it a constant current source? So all these questions come up, and that's how the labs are built for this educational kit. As I mentioned before, the point here is not to give students a cookbook so that they can put some ingredients and they can prepare a dish. We want to make them Michelin star chef. We want to make them curious minds where they want to explore on their own. And the location is not the barrier. They can be at a cafe drinking coffee and trying out this kit, or they can be in the remote part of the world where not all the resources are fully available. They can take help of this kit and learn power electronics from a very practical standpoint. We hope that you will be a part of our journey of as we grow this kit into a broader scale, as we scale up. I hope that you will be not only looking at this as a thing where you will just do it for the sake of your school or as a student, but you will be taking part of this open source platform where you will be adding, hey, I want to do this, I did this, look how it changed, or this characteristic was not there and I figured this out. So we are looking forward to be a part of a team where we take this IEEE PELS University Lab Kit to the next level, and students around the world get to the benefit of using this practical hardware to understand power electronics. So all the best, and stay tuned as we post more and more labs and we grow this website, as you will see in the forthcoming weeks. Good luck. I'll see you in another video.